Hello everyone, this is our work estimating the confidence of speech spoofing countermeasure. The background of this work is for speech anti-spoofing. So we want to build a countermeasure to tell whether the input waveform is bona fide or spoofed. This application is quite important because nowadays spoofed audios or deep fakes may be used to fool the human beings. So we need this kind of application to protect the human users. In the research community, we usually formulate this as a binary classification problems, and we normally use deep neural networks. Now, suppose we are giving a trained countermeasure, giving an input waveform. If the countermeasure says, okay, it's bona fide, the question for us as users is how confident the countermeasure is and whether we should trust the decision of the countermeasure or not. So ideally, would it be better if the countermeasure can say something like, the input is bona fide, but I'm not so sure. So this is important, especially when the countermeasure is not confident. In this case, we should avoid making any decision. We may also ask human experts to analyze the input waveform. So based on this motivation, our question in this work is to ask whether we can build the confidence estimators for the countermeasure. Do they work, and whether they are useful if they are combined with the countermeasure. Of course, this work is related to the classic work using log likelihood ratio, but since we're using deep neural networks, most of the methods here are from those deep learning literatures. Okay. I will explain the methods we investigated. First, let's look inside the countermeasure. Usually, we have the feature extraction followed by the scoring module. The output score will be compared with the threshold to give us to make a decision. Ideally, the score distribution should look like Gaussian distributions. And in this case, we can see, okay, this countermeasure is not confident if the score is close to the decision boundary. However, the reality is when we are using deep neural networks, the countermeasure might be overconfident. So the score distribution may look like binary distribution. From this kind of distribution, we cannot get meaningful confidence information. So facing this issue in this work, we add additional confidence estimation block to the countermeasure. We hope we can better estimate the confidence score, C here. We investigated a few confidence estimators that can be plugged into this framework, and I will explain them one by one. The first method is based on the softmax output. In the countermeasure scoring, for example, we may use Cn, Rn followed by temporal pooling, linear layers. From the linear layers, we get the logits to the softmax function, L1, L0 here. We can use these logits to compute the probability, giving the softmax function. During the scoring stage, we compute the difference between the two values. So this is equivalent to the logits of the logistic regression. So based on this value, this L1, L0, we can compute the confidence. Specifically, the first method recomputes the two probabilities in the inference stage through the softmax. It takes the maximum value of these two as the confidence score. Intuitively, if the countermeasure is not confident, these two values, P1 and P0, should be close to 0.5. And the value of C here should also be close to 0.5. In contrast, if the countermeasure is confident, then the confidence score should be close to 1. So this has been used as a baseline method for outlier detection in the deep learning community. The second method also uses the logits, but it uses this equation to compute the negative analogy score. This method was proposed in the literature on outlier detection. Well, the same as the previous method, they are non-trainable and they can be directly used in a pre-trained countermeasure. The third method does not use the logits from linear layers, but you use the output from the temporal pooling layer. So no matter how long the input audio is, the output from this temporal pooling layer has a fixed number of dimensions. So we can use a simple network to convert this vector h into the confidence scores. So this module is trainable, and it should be trained together with the rest of the countermeasure. During training, we need a special training criterion so that we can train these two parts together. Due to limited time, I cannot explain the training criterion here, but you can find the details in the reference below. So these are the three methods I'd like to mention in this presentation. In the paper, we have two additional methods, although their performance was not so good. We can discuss these two methods in the poster section. Okay, let's go to the experiments. For the experiments, we followed our work and used the LFCC LCM-based countermeasure architecture. During training, the countermeasure can use either the additive margin softmax or plain softmax. In terms of database, we first used the anti-spoofing 2019 logic axis database. Additionally, we included data from the Blizzard challenge and the worst conversion challenges. Both contains natural data or bona fide data also. The third source is the ESP.NET open source TTS toolkit. So we get spoof data from this toolkit, and we collected the bona fide data from the corresponding database, the OJ speech. So based on this data, we prepared a few training sets and test sets. By combining the different training and test sets, we can simulate different application scenarios. For example, when we use T1, the training set T1 and test set E1, we're actually simulating the standard protocol from the SUS challenge. We treat the unknown attacks as unknown trials for the confidence estimation. So this is the first case. In the second case, we replace the unknown trials with the VCC data. So in this case, this test set E2 is more difficult because the unknown trials have different acoustic conditions and also languages. They also contain more advanced worst conversion systems. Here are the experiment results. It's a big table. I cannot explain all of them, but let's look at the subpart of this table. This is a subtable based on the training set T1 and the test set E1. These two columns show the EER without considering the confidence estimation. So it's just usual EER computed on the test set. These three columns on the right-hand side show the confidence estimation method performance. The false positive rates, the arrow under curves. Here is another column which shows the EER after removing the low confidence test trials. So the three columns on the right-hand side tells the performance of confidence estimation, while this EER, this special EER, shows the performance of the countermeasure after we take the confidence scores into consideration. So I will explain this later in the presentation. Okay, let's look at the results. This results is for the countermeasure using additive margin softmax. We can see the score distribution of binary. If we estimate the confidence based on these scores, you can see the confidence is close to 1 for most of the samples. To better show the interaction between the countermeasure score and confidence scores, I will plot the figure in a two-dimensional space. So as you can see here, clearly most of the samples have higher confidence scores, no matter what the value of the countermeasure score is. Especially for this unknown spoofed samples that have higher confidence and also higher countermeasure scores. It basically means the countermeasure says these samples are likely to be bona fide, and I'm quite sure. But in this case, the countermeasure is making a wrong decision. Next, we can plot similar figures for the other two types of confidence estimation methods. Again, we can see the score distribution or binary. However, in this case, we can see the confidence branch can estimate the confidence scores quite well. We can see unknown spoofed trials have lower confidence scores as expected. But from these samples, we can also understand that countermeasures are overconfident when using the additive margin softmax. We need, for example, the trainable approach, the confidence branch, to better estimate the confidence score. Again, we can plot the similar figures for the countermeasures using plain softmax. So in this case, as you can see, the countermeasure scores are more like Gaussian distributions. These countermeasures are not overconfident, and there is a strong correlation between the confidence and the countermeasure scores. Based on this case, even the non-trainable estimators can achieve quite good performance. As you can see, for example, in this energy-based one, most of the unknown trials will have a lower confidence scores as expected. Now, let's look at the figures on the test set E2. In this case, unknown trials are replaced with those from the verse conversion challenge, so they are more challenging. But we can see the score distributions. The countermeasure score distribution are still like Gaussian, and we can see the correlation between the confidence and the countermeasure scores. So in this case, the energy-based confidence estimator and the confidence branch can estimate the confidence for the unknown trials reasonably well. So we can see these two methods are promising to estimate the confidence for the spoofing countermeasure. So, is the confidence estimation useful? Here is one example. First, let's consider the usual case where we compute the ER over all the samples. So in this case, all the bona fide sample and the spoof samples. We get an ER of 5.5% in this case. Now, if we remove the trials with low confidence scores, we can get this new ER, which is about 2.8%. So this is lower than the previous case because, as expected, after we're removing those low confidence trials that are difficult to classify, we can get better ER to better classify the remaining trials. So this is one example where the confidence estimation can be combined with the countermeasure in a meaningful way. So in quick summary, here we compared a few confidence estimation methods that can be directly plugged into the countermeasure. Their performance, of course, depends on the countermeasure. Usually the AM softmax based countermeasure are overconfident, and based on this kind of countermeasure, we cannot really estimate good confidence scores. If the countermeasure use plain softmax, then we have a higher chance to get better confidence scores. Especially the energy-based score, the non-trainable one, and the trainable confidence branch can be used for this purpose. Whether they are useful, yes, at least in this simple example, we can show how the countermeasure can better classify the remaining samples that have higher confidence scores. A more advanced usage of this confidence estimation is for active learning. As you can see from this picture, we select the low confidence trials, add them back to the training set, and fine-tune the model again. So this work is published on the archive. If you're interested, please find details in that paper. Okay, that's all the contents. Thank you.